Welcome to the session for AI-based library development on HMOS. Thank you all for joining. So before we dive into the details of library development, let us go through a few stage settings. I understand many are from AI background, but the initial 2 to 3 slides are helpful for those who are from non-AI background. So please bear with me. So AI or artificial intelligence, as we all know, I'll try to keep it as simple as possible. Just to brief about it. So this slide actually depicts almost all aspects of AI system. So in an AI system, first we make sure the machine is reading all the contents of the book, which is the data in usual sense. Intelligence it can during that phase. Once the learning is complete, we can ask the necessary questions, be it in the form of images or voice or videos or text. Machine, then it will try to find the appropriate answer from it based on the intelligence gathered earlier. So there are many deeper concepts involved in it, and there are a lot of various arguments are here. Let us not go much into it. I just want to keep it at the high level picture. So let's move to the next one. Now, in order to understand a few basic and necessary concepts of surrounding AI, let us go through a very famous example of linear regression. So let's see this image. As you all can see here, uh, it's a random XY plotting of two data points. Let's assume that the y-axis represents the price of a house and x-axis represents square feet area of a house. Now, this I assume we all agree that when the square feet area of house increases, the cost also increases. So the plotting will be accordingly. Now, by looking at this picture, can we find any relationship between the two data points, which is the price of a house or and square feet area of the house? Is it possible to find a relationship? Can we generalize the relationship so that it can represent all the data points, which the X marks what we are seeing here on the plot? When we get area of the house, can we predict the cost of the house? So these are the questions that comes to mind. Then we can think of AI. So AI can help us here to generalize it and give us a graph like this. So when we get this straight line, we can say that we have generalized and form a relationship between the two data points. And when we get the x value, we can predict the y value. When we get a y value, we can predict the x. Now here it may not be 100% accurate, but it's a close approximation. So that is what the AI is all about. Now, there are three major, key founding stones in AI. That is data, training, and inference. Okay. So model is the byproduct of training phase, which will be used in inference. So these two are closely dependent. So here, inferencing means executing the model, which is produced during the training phase to get the output from the desired input what we have. So in this picture, as we can see, the y equals to mx plus c is the generalized relationship that is learned during the training phase when it was trained with all the data entries that was present earlier with us. So here the data are your price of house that is in y-axis and the the square feet area of the house that's on the x-axis. And the m and C are the trainable parameters which can be finalized through training stage. Once training is complete, the model will be produced, which will represent the equation, the blue highlighted color, that's y equals to 2x plus 1. So this is the most suitable generalized equation which we can form out of this data. So this is the relationship between these two data points which the machine has learned by training it through the data what we have provided. And once the training is complete, this generalized equation will be formed. So this equation will be represented in the model. Okay, so let's not discuss how it is represented because that will be out of the scope here. We just want to understand high level. So we just assume that this y equals to 2x plus 1 is represented inside the model and move forward. Now, these are some example of various famous models that are used frequently. So we can just have a look at this. Now, as I have explained, there are three major aspects in an AI system: one, data, then training, then inference. So, at a very high level, we can divide all the activities involved in a complete end-to-end, AI system into two phases. One is the research phase, and another is the deployment phase. In the research phase, one has to develop the model architecture which is most suitable for the objective at hand. Train multiple times and validate whether correct model, the model which we are training is able to reach the optimum result. If it is not able to reach, then again we have to change the model architecture and retrain it from the scratch. So for this kind of activities, there are even many more other activities. So I'm not putting those details here. I'm just sharing the brief of it. So for this type of activities, framework like TensorFlow, PyTorch, Cafe, Keras, these are used, frequently. But these are not our focus area. Our focus area is deployment. So in case of deployment, we need a framework which can highly optimize the model execution on the intended target. The optimization of a model can be in terms of execution time taken end to end, or the runtime memory consumed, or the disk size. So various targets or hardwares which has many different requirements also. Some may have low processing capability, some may have less RAM size. So we need a framework which can universally optimize for any models from any framework like TensorFlow, Keras, PyTorch. Also consider all the hardware constraints. In this slide, I don't want to explain about HarmonyOS because there has been a lot of already lot of many sessions on this. I just want to highlight here that our HarmonyOS is multi-device capable. Hence, this requires a framework, AI framework, which can support model optimization for deploying in various targets or devices, be it mobile or IoT devices or wearables or PC or tablet, etc. So that's just I wanted to highlight here. So TVM. So based on the requirement, what I had explained earlier, uh, we had chosen TVM as the best fit for our requirement. So here TVM is the framework. That's full form is a Tensor Virtual Machine. It's an open source compiler stack for machine learning models, which has many different optimization techniques at various stages, like your target agnostic optimization or target specific optimization. Even there are other stages. Let's not look into the internal components of TVM. We can get a model from any research-oriented framework, like I told, TensorFlow, PyTorch, and optimize it for our intended target by compiling it through TV. Post compilation, we can use the artifacts produced by TVM for inferencing or executing on intended task. Now, how this inferencing is done, that we'll see in the following slides. So, there are basically three artifacts generated by TVM. One, as you can see on this side, the diagram, there's, for example, you have a TensorFlow-like model, and you want to compile it through TVM, then the TVM will generate three artifacts. One is your kernel, that's a .so file. One is the graph that will be in JSON format. One will be your pre-trained weights that will be in your binary format. So these three artifacts will be generated once you compile it through TVM, and we'll use these three artifacts and execute or do the inferencing on the target. So TVM has already exposed a lot of user-friendly Java APIs, and we'll see how to use them, to how to use them in our app development. So here in this snippet, you can see this is a snippet from one of our library which we have developed using TVM. Here you can see the three files we have taken and inbuilt into the workspace. So the deploylib.so is the kernel, graph.json is the graph file, params.bin is the weights, that's the binary file. Okay, so in order to do the complete end-to-end inferencing, we'll go step by step how these artifacts are loaded and what steps are needed to complete the inference. First, we need to load the graph, which is in a JSON file format. Here, as you can see, the first one, that is the model graph file. That is a JSON file I had shown in the previous slide. That is being loaded here in this section. Next, we need to load the kernel file, that is the lib.so file, that is being loaded here. Once these two are loaded, we need to create the module, which is an executable complete package in TVM context. Using the graph and the kernel, we can create this. So that is being done in this section. Okay. So once this is done, let's move to the next step. Here, once the module is created, we need to load the pre-trained weights. So in this snippet, we are loading the pre-trained weights using the load parameters API. So you can see here, this is the model params file part. That is nothing but the binary file, which I had shown in the previous slide. And here it is calling the load params API, and this is a pretty standard format to use that API. This is the way it will load it into the module. Once all parameters are loaded, we need to prepare our required input for the model or the module in TVM, and feed it into the module which is created. So TVM here expect all inputs in ND array format. So this ND array format is it's a tensor representation in TVM. So it has a lot of inbuilt APIs to load from different types of buffer and exporting into different types of buffer. So we can experiment with those things. Basically, we need to create ND array for all the inputs required, and that ND array will be fed into your TVM module. So we prepare the ND array from input like images, text, audios, and videos. Once these all ND arrays are created, we can call the set input API to feed it into the model. Here you can see in this example, this is example from my our style transfer library. Here it required two input. One is your the content image that, and one is your style image. So this is the way you can set two inputs here. ND arrays are created before that. Once these two are created, this set input are called with those two ND arrays. So this is the standard way to feed the input into the TVM model. Okay. So once the inputs are ready and we have fed it into the model, so we are ready for model execution or inferencing. So in order to execute it, we need to call the run API here, as you can see, and the inferencing will be done. Okay. So once the inferencing is complete, now we need to fetch the output. So in this snippet, it is shown that how to get the output from the model executed. So it need to call the get output API, and again here it will be in NDARray format. So we need to convert it to our native data type, because NDARray as it is we cannot use for our post processing. So we need to convert it either into float or integer or uint8 based on your model output. You need to convert it. So there are a lot of inbuilt APIs, as I told, in NDRs. You can utilize them and convert it. Here it is converted to float array, as you can see here. In this example, it was needed to be converted to float, so we are doing that here. Okay, so this ND array to native data type conversion, we can do it through our inbuilt APIs. Okay, so these are all the APIs that we need to know for a complete end-to-end inference using TVM. Now let us go through one short demo where we can see how to develop AI-based library using the APIs exposed by TVM on HarmonyOS. So I'll just play offline. Welcome to the demo. In the last slides, we have already seen the APIs exposed by TVM, which enables user to do an end-to-end inferencing. In this demo, we will see how those APIs are used to create an AI-based library on HarmonyOS. We have developed a library known as food classifier, which can classify up to 2000 plus food categories. Now this model used here is borrowed from TensorFlow Hub, which is an official repository from TensorFlow for various pre-trained models. Now we'll see how this app is developed using TVM. First, let us check the TVM artifact, which are basic need to do the inferencing. Now you all can see here the three artifacts as I explained in the previous slides. There will be one kernel library, that's a .iso file. There will be one graph, which is a JSON file. There will be for parameters, which is a binary file, and this is the food labels, which will be used to post process the output from the model and map it to the respective label which it has predicted. Now classifier here, as we can see, is an HarmonyOS module.
which is same as any regular HarmonyOS library. So let us go through the code now. As you can see, all three artifacts are placed in the raw file directory under the module. So we need to use the relative path here in this format to access those files. So the three artifacts, as I already told, the graph.json is under the raw file directory, the deploylib.so, which is the kernel.so file, under the same raw file directory, and the parameters, which is the binary file, under the same raw file directory. Now these three files will be loaded in from the artifacts raw file directory in our app runtime. Now let's see where it is loaded. So here in this place we are loading the graph, which is the JSON file, and we are using the standard APIs exposed by HOS to read the raw file entries. So once that is done, the next we will load the kernel library. So this is the place we are loading the kernel.so file. Once that is done, we need to create the inference or the execution engine, which is known as a module in TVM context. So this is the API, this is the standard API exposed by TVM we are using here to create the module, and the graph which is loaded here and the kernel library which is loaded here are used to create the graph execution engine. So once that is done, once the TVM module is created, next we load the parameters, which are nothing but the pre-trained weights. It is a binary file. So we'll use the load params API exposed by TVM and load the parameters into the module, so which I already shown in my last slide. Now we need to prepare our input tensor for inferencing. Here in our case, the input is an image which will have any food in it. Some models need certain pre-processing of input data like scaling, cropping, transposing, etc. So we can do that here before feeding the input to our inference engine or the module which we created earlier here. So we are loading the JPEG image using the standard API, again that is exposed by HOS media. So here we are loading it and loading it into the pixel format. Once the pixels are loaded into an integer buffer, we all know that the color image will have 3 channels, which is RGB. So we are converting the pixel values which is in the integer buffer here into the RGB format, because our model expects the input in RGB format. So we have done that here. Once that is done, we need to create the ND array out of the RGB image data, as TVM expect the input tensors in ND array format. So this is the place we are doing it. So this is the standard way of creating the ND array. So here we can see the ND array is of UINT8 type. Okay, so this model which we have used is expecting the quantized form of input data. So that's the reason the type is uint8. And once the ND array is created, we can call the set input API from TVM to feed the input to the module. So this is the way to do that. So this is exactly same as I already explained in the slides. So once the set input is done, we are ready for our inferencing. So we need to use the run API, which is exposed by TVM, to execute our runtime engine. Once this is done, our inferencing is complete. So post this execution, we can fetch the output in ND array format using get output API exposed by TVM. So again, it is in ND array format, and we need to convert it into the native data type which we expect to process it. Now in this case, we are expecting a byte array. So this is the way we can convert from ND array to byte array. That is done here. Now few models need certain post processing of the output data. As in our case, we need to get maximum scored level or the class which the model predicted for the given input image. So here we are doing that post processing and mapping the highest scored level and displaying the output. So now our end-to-end inferencing is complete. Let us see how this classifier module or the classifier API exposed by this HarmonyOS library is used. So let us see one short example here. So in this case, we can see here we are creating the classifier instance and providing the input image, which is in our case it's an image of omelette. So we are giving the path where the image is stored. So this path we can see here, the image is stored in the base media folder. So we need to provide that during creation of the classifier library instance and other relevant information that is expected for the execution. So once the instance is created, it will auto execute the complete model end to end for the image provided, and we can fetch the output using this API get output that is exposed again by the classifier module. So now we got the label, and the label we can display it to the user. So now let us run this app and see how the food image is classified. So let us load the emulator. Just allow it. Okay, so our emulators are ready. So we'll choose this emulator. Let's load it. Okay, so our emulator is ready. I'll just maximize the screen for a better visibility. Okay, now I'll trigger the app execution. So we can trigger it from here. Now it will compile the app and it will push it to the emulator, then it will execute it. So let us wait for that. Okay, compile is done. Now it is pushing the package into the emulator. Okay, so the app is loaded now. Now this is the welcome page for the app. So let us click it, put class of app. Now here we can see we have three options to choose, three different images. We can choose any one. So let us choose this picture. Okay, so the picture is of a sandwich. Now our model executed and it has predicted also as a sandwich. So our model execution is done. So this is how we can develop an AI based library. This is the end of the demo. Thank you.